Hello, my name is Scott Bryson, and I am an applications engineer for Texas Instruments current and position sensors. In this video, we will discuss how inductive sensors can be used for absolute angle measurements as well as for incremental encoding. Rotary encoding is a method used to detect position changes for a rotating object such as a wheel or knob. For example, we might want to monitor absolute alignment of a wheel where we need to determine any angular position precisely, or we might want to observe fixed incremental steps on a knob in either the counterclockwise or clockwise directions. These functions are typically performed using a mechanical system which is prone to wear out over time, or with a Hall effect sensor, which might be defeated by a nearby external permanent magnet. In this video, we will discuss how this function can be achieved using inductive sensors to provide a solution that is durable, robust, and immune to interference from a fixed permanent magnet. Inductive sensors will produce variable output with respect to the proximity of a conductive body. The inductive sensor drives current into a coil which is part of an LC tank and then monitors the resonant frequency of the LC pair. This current produces a low-level AC magnetic field which generates surface-level eddy current in the metal in opposition to the current in the coil. This effectively reduces the inductance of the coil and changes the resonance of the LC tank. Here we will see that as the target is moved away from the sensor coil, that there is a measurable change to the effective inductance, and that this reduction is less dramatic as the distance increases. Although this is the typical arrangement, we can also set the metal target to a fixed distance from the coil. If we were to move the target laterally instead, we might design a target which changes the surface area exposed to the sensor as it moves. We can utilize this approach to enable rotary applications. Consider first a diamond-shaped metal target which has a linear taper to the body width. In this top-down view, we see that the width of the target varies linearly with respect to the length of the target. If we were to pass this above our sensor coil, we expect a sinusoidal output as the width of the metal over the sensor coil changes. As the width narrows, there will be less eddy current in the target surface, which reduces the influence on the coil. For this example, the LDC output has been normalized and centered to 0, although in reality, we would expect the amplitude and level to depend on the air gap, coil and target geometries, and the target material. While this target may be useful in linear travel, we can modify this shape to be more suitable for rotation. If we were to distort this shape by wrapping around on itself, we can produce a circular shape where the width is proportional to the phase angle instead of the length. With this new target, we can rotate the target in place rather than moving it linearly over the sensor to achieve the same sinusoidal behavior as the output. The sensor coil will continue to experience the same mutual inductance with the target, and we therefore expect the same output behavior as observed previously with the diamond shape. From here, we can create a robust quadrature output by using two differential pairs of sensor coils. Observing the outputs within each pair differentially helps to normalize the sensor output for the best performance, and using a second pair 90 degrees out of phase allows us to calculate angle. If we place each coil 180 degrees separated from its mate and 90 degrees separated from the other differential pair, we can achieve our desired output behavior. As the target rotates, we can monitor the differential output for each pair. Over the course of one full rotation, we see that one output will behave as a sine wave, while the other output behaves as cosine. With the two sinusoidal outputs 90 degrees out of phase from each other, we are then able to use the outputs to perform calculations of the arctangent function to determine the absolute angle. When performing this calculation, additional calibration and processing may be needed to help account for assembly variation and mechanical errors. For more details implementing this solution, please review our TI design 1-degree dial using the LDC 1314 inductance to digital converter. While some solutions require absolute angular accuracy, other applications might only require discrete incremental steps. We can adopt a simplified approach to the method already discussed by quantizing the angular steps. This does reduce overall resolution, but can simplify output calculations required to determine position. Instead of varying the width of the metal target, we can replace the previous metal target with the gear shape pattern, which features equally sized teeth and notches. Using this method, we can monitor outputs which are formatted to generate a binary output, which is either high or low. As a trade-off, we will not have exact position information at power-up, but as the outputs are monitored, we can easily determine rotation speed, direction, and discrete changes in angle instead. To begin, let's first consider just one sensor pair. We continue to need each coil 180 degrees out of phase with its mate. If we let each tooth and half of each of the adjacent notches represent one full output cycle, then we might subdivide this region into 4 positions that each represent 90 degrees electrically. With this format, the coils require a separation of 2 spaces to achieve our desired 180 degree offset. When sensing absolute angle, we measure the difference in magnitude for each pair, but for this method, we need only to logically compare the output states. We observe these states as the object rotates. If we now add a second pair 90 degrees out of phase, we can achieve a quadrature output with a resolution of 1/2 the width of each tooth. For this pair, we will want to place the coils in the unused slots from our previous region. But to avoid routing conflicts from neighboring coils, we should shift these to another unused region of the metal body. We can now track the comparison output of each pair as the metal body is rotated. When tracking both signals together, we will have 4 distinct output states per tooth. In this example, with 8 teeth, we expect a total of 32 positions. Each position change represents 11.25 degrees of rotation. To determine speed, we simply need to know the pitch between the teeth and the rate of the edge transitions. We can determine direction by comparing the phase of signal A and signal B. In this example, we see a rising edge on B before the rising edge on A, which represents clockwise rotation. The opposite will be true for counterclockwise rotation, where the rising edge on A is first. Discrete angular position is then easily determined by tracking the edge transitions combined with the direction information. If a counter is incremented at edge transitions during clockwise steps and decremented during counterclockwise steps, we can easily track the approximate angular position of the object. Due to physical geometry of the metal target, a circular coil pattern is not ideal for this application. This is especially true as the number of positions increases. More incremental positions will result with smaller coils as the target size decreases. If the coil size becomes too small, the inductance of the coil may not be within the operating region of the inductive sensor. Instead, a trapezoidal coil is better suited for this example. Here we can maximize the coil size and the space available to achieve an inductance capable of detecting the metal target. For more information regarding implementing this design, please review our TI design, LDC0851, Incremental Rotary Encoder, for more details on this implementation. Also available from TI.com are various design tools which are useful when designing using inductive sensors. The Inductive Sensing Design Calculator tool helps to determine sense coil parameters quickly and provides guidance regarding possible device performance. Also available are LDC Sensor Design and LDC Target Design application notes, which describe the inductive sensing design process in detail. When the use of a magnet is permissible, we also recommend you consider our Hall effect sensor products for this type of application. More details are available in our magnetic sensors videos available at training.ti.com. To find more inductive sensor resources and products, visit ti.com/sensors/specialty sensors/inductive/products.html.